My name's Hayden Burnham. Okay, so we'll get started here. So the first thing I want to talk about is what is the difference between CT and DT, or continuous time and discrete time signals. So a signal is, pretty much kind of like where you've had these x of t and t graphs that you've seen in like your other math classes. So it's basically, that's what a signal is, and there's these two types. So continuous type is, it has a continuous line where we know the value of the signal at every point in time. So like a mathematical function, or what you're usually used to dealing with in like a math class would be a continuous time signal. Well, a discrete time, we only know the value of a signal at given times n. So it's more like we're just getting pieces of a signal it could be every second or every millisecond or whatever, but we only have the signal at specific times. And these two fundamental differences is very important to understand, because later on when you look into things, it has a lot to do with how signals are interpreted, particularly how computers interpret signals. Because in the real world, computers can't really work in continuous time. They work in more discrete time. So it's good to understand the difference between these two. Okay. So the next thing I want to talk about is some of the things that we can do with signals. So signals can be changed, altered, shifted, all sorts of different things, so that we can get different results or manipulate to our will. So the first one I kind of wanted to just go over is time shifting, which is really simple. All it is that you're taking, let's say, signal x of n on the left, and we're just transforming it to signal x of n minus 3 on the right. And the math here is pretty simple. If you're just plugging in n minus 3, it's going to shift the signal to the right 3. If it was n plus 3, it would shift the signal to the left 3. So that's where it's kind of confusing, but it's usually the opposite. So if it's a minus number, it's shifting to the right. If it's adding a number, it's shifting to the left. Okay, then the next thing to understand is something we call time reversal. So time reversal is also really simple. It's basically just taking the value of t, in this case I use continuous time, and you're just negating it. And what it does is it just flips the signal over the y-axis. So that one's not too hard, easy to understand. Okay, and then the last one I want to go over is something called time scaling. And this is one that's kind of confusing. So here on the far left, I have x of t. So this is our signal that we're just given. And if we take the inside of that signal and we multiply the time by 2, or we do it at x of 2t, it does this thing, normally you would expect it to stretch out, but in this case, it actually will cause the signal to exist over a shorter span in proportion to whatever number you multiply. So since this one's 2t, it's basically going to half the signal. And the opposite is true for here on the far right, where we have x of t over 2. That will stretch the signal out over, it will basically double the duration of the signal. Okay, so far for everything I've covered, is there any questions or maybe anything I should go back over?
No, I'm good.
Good. Okay. All right. So now we're going to move on to the real serious part of this conversation, is what is a system? So a system, I think people like to think of systems kind of like equations, where you have like a y of t equals an x of t plus all of that. But it's kind of, you have to be careful to remember that, it's kind of a system of where, where y and x are dependent variables and t is our independent variable. So we're dealing with 3 different variables in one system or one equation. So basically, but at the same time, x of t is an independent variable to y of t, but t is an independent variable to x of t. So, usually when we're dealing with signals, we're more concerned with the system where the actual signal is. So for x of t, for this one, we're just told that y of t is equal to x of t plus 3. So basically what that would be is that would just be whatever signal x of t is, we would take all of those values and add 3 to them for all time. And on the bottom one, I have y of t is just equal to a time-shifted x of t. And now this is also true for discrete time. It works the same way. Okay, so now understanding signals too, one of the things that helps us a lot is also to understand complex numbers. Okay, so a complex number, if you've taken some particularly modern differential equations, a complex number is given by the square root of -1. And in many math classes, they call it I, but in engineering, it's referred to as J. And the reason for that is because in particularly electrical engineering, sometimes when we're dealing with a variable, we're mixing it with, or using it to calculate current, which is represented as an I. So to have 2 I's is not good. So a lot of engineers prefer to use J as the imaginary number instead of I. And a long time ago, there was this guy named Euler, who was a famous mathematician, and he figured out by doing some series, I'm not going to go into how he figured it out because it's a little beyond the scope of this, but he figured out that if you take the exponential of j to some angle, that is going to be equal to the cosine of that angle plus j, the sine of that angle. Now this formula here is called Euler's formula and is incredibly helpful, and it helps us understand how to relate an exponential to cosine and sine. It helps us to break apart signals, and it will help us lead to some of the transformations and other things we'll do with signals later on. And something that you can do using this previous equation, you can separate and do all this math, and eventually you can come to conclude that both cosine and sine can be represented as these formulas of exponentials and imaginary numbers. And so this is also really helpful in understanding, and this helps with the course a lot. Okay, so before we move on, any questions or anything? Oh. Sweet. Okay. So move on. Okay. So we've talked about systems. I'm going to go a little bit more into detail about some properties of a system. And we're really concerned with 5 different properties. So we have, when a system has memory versus when it's memoryless, what is a causal system, what is a time-invariant system, and what is a linear system, and also what is a stable system. And all of these are important, but particularly that we really want to understand is what is a time-invariant system and what is a linear system. Because a combination of these 2 properties helps us to develop a lot of systems that let us do a lot of stuff later on. And pretty much all of Signals and Systems 1 focuses, after you learn this, it focuses completely on linear time-invariant systems. And so, but basically understanding these properties can help us to understand, how signals work, and it helps us understand some of the advantages and disadvantages in a signal or in a system. And it helps us to just work through different problems that we might approach in engineering. So the first one is, what is a memory versus a memoryless system? So a system has memory, we say, when the system is retaining or storing previous inputs or future inputs, including the current time. So basically, if you look over here at my examples, we have y of t equals x of t minus 3. So that first part, x of t minus 3, that's going to be the value of x at time. So if it was a memoryless system, it would only do it where it's the current t. But x of t minus 3 is wanting the x value 3, minus 3 earlier. So that could be 3 seconds earlier, or 3 seconds, or 3 milliseconds earlier, whatever. But it's requiring a previous value. So that means that this system has to have memory. It has to be storing all of the values of the signal. And that's the same with the bottom one where we have x of n minus 2. A system is memoryless if it's the opposite. It only takes x of t at the present time. So that would be there's only a singular t. And even this x squared of t, that's still memoryless because you can just take the current value and just square it, and that still gets you the right answer. Another good example of a system that requires memory is if you had like a y of t equals the integral of x of t, that system, even though it's x of t, it would still require memory because in an integral, you're taking the values of the x of t from one point to another point. So that would require you to have stored or to have remembered all of those values. Okay, so then the next one is causal. And now causal and memory, they kind of work in the same boat, or they're kind of the same, where a causal system it's kind of like a system that has memory, but only of the current value and of previous values. So it's basically like you've memorized everything, or the system has all the information of the past and the current and the present, but none for any future values. So like the top system here is wanting to use x of n, so let's say like n is 0, right? And then the other system is x of n minus 2, so that would be x at negative 2. So that's a current value and a past value. So in this system, it would be causal because we aren't requiring any future values. Well, here on the bottom, it's wanting an x of n plus 2. That's a value that's in the future, a value that hasn't been recorded yet. So we would say that this system's non-causal. Okay. Now the next one, this one could be a little confusing. So this is saying that a system that is time invariant is if its behavior and characteristics remain fixed over time. So basically how this one works is if you were to take your x of n, your signal, your input signal, and you were to shift it, do a time shift, your y of n, your output signal, would also be time shifted for the exact same amount. So that's like what's represented here on the bottom. We have like an x of n minus q is going to, after it goes through the system, is going to give us a y of n minus q. If that did not happen, we would say a system is non-time invariant. So basically, a change to the independent variable inside of x will lead to the same change of the y, or to the output signal independent variable n of a y. So that would be the difference between the two of these would be. And this one is also a little tricky in how you would figure out if a system is time invariant, because here I'm going to actually stop sharing that real quick. I'm just going to show it on my Word document. So let's say you have an x of n. Let's do y of n. Y of n equals x of n. x of n, let's say plus 3. So we want to know if this system is time invariant. So we want to know if the system is time invariant. So the first thing that you do is you take in n and you would change it to, let's say, n minus n naught, right? That just means I'm shifting the system. So you would have x of n minus n naught. And that would be plus 3 because it still would be there, right? So that's the first thing you do. Then the second thing you do is you would put it, you do it again, but this time you're going to do it as if it's in the parentheses, right? So you're going to have n minus n naught plus 3. Now you look at these two equations and you ask if they're equal, then it must be time invariant. If they are different, then the system is non-time invariant. And that might seem, well, wouldn't that be the case in all situations? So I'm going to give us another example. Let's say instead it's 3 minus n, right? So in this situation, we would have 3 minus n naught, right? But in this example, we would have 3 minus n naught, right? Now, the difference between these two is these two are in parentheses, right? So you would have to carry that subtraction to both terms. So then you would end up with x of 3 minus n plus n naught. And now this one and this one, they are different values. They are going to return different amounts or different signal samples. So we would say that this signal here is not time invariant. This is not a system that you'll have a same change to y if you do to x. I hope that was clear. It's a little bit confusing sometimes, but basically, yeah. So that is basically what time invariance is. Okay. So that's basically the test. Is you would plug in, you would take n and you would subtract an n naught, and then basically you do the same thing, but you put parentheses around it, and then you would calculate and see if it's the same thing. And if it is, then great. If it's not, then it's not time invariant. Okay, linear. So linear, I think we talk about linearity a lot, especially in like modern differential equations. I think a little bit of Calc 3. But basically, a system is linear if it obeys two other properties, or two other rules, you can say. So the first property is the system additive? Meaning if I have a signal x and a signal y, and let's say signal y can be broken up into a y, or we can take let me start. So if we can take the x of t, and let's say we plugged in a certain value for t and we got x1 of t, right? So that's x of t at a certain value. And then we plugged in a different value and we got x2 of t. If I was to plug in those values at into y of t, and I was to add them together, and same on the other side, then would they be equal to each other? And if that's true, then the system is additive. For the second part, we have the rule of scaling. And basically scaling is saying, if I take the right side, right, if I take x of t, if I was to multiply it by a certain value, and we'll just say a constant value, would the output be the same, just multiplied by that constant value? So to be linear, it has to obey both of these rules. So there's kind of this more clever, at the very bottom, you see that there's this clever way of where we can kind of combine all the rules together. So basically, if you have a system that obeys this last part, all of these rules, that you have a system that can be rewritten as this, then that system is linear. Okay. Now lastly, the last important one, but also the most confusing one, is stability. So a system is said to be stable if small inputs lead to responses that do not diverge or grow without bond or blow up. So in Calculus 1, or actually I think it's Calculus 2, when you're first learning about like integration and stuff, sometimes you have to solve these problems where you have to determine if a signal converges or diverges. So basically a system that diverges is that the system, if you put in an input that's very large, is the system going to go to infinity? Or even if it's a small input, is the system going up to infinity? So how this math works over here is we have y of t equals x of t times the cosine of 3t. So for the first part, we're going to assume that x of t is a bounded number, or basically x of t is going to be less than infinity. It's going to be a finite number. So, or at least the absolute value. So basically what we can do is we can take the absolute value on both sides, and we can look at cosine of 3 of t. And we can ask, is this value, or would this always be bounded? Is there any value of t that would make the cosine of 3 of t go to infinity? And if you understand how a cosine wave works, that's never going to be the case. Cosine is always going to be between 0 or between 1 and -1. It's never going to be higher or lower than those two. So considering that x of t is always going to be less than infinity, and cosine of 3t is always going to be less than infinity, then we can say that y of t is going to be bounded, and therefore that this is a stable system. Now, if it was, instead of cosine, if it was like the exponential to the 3 of t, well, we know as t gets larger and larger that that's going to go to infinity. So in that case, the system would not be bounded. It would not be a stable system. Okay, so out of these 5 rules and everything, is there any questions or any you wish for me to go back over? Sweet. Okay. Now I do have some practice problems, and I can give you some time to try them on your own, or I can just go ahead and go over them, whichever you prefer. Okay, so the first one, we have, y of t equals x of t minus 2 plus 2 minus t. Okay, so what I meant was we're going to decide on the properties. Is these systems, are they memoryless? Are they causal? Are they time invariant? Are they linear? Are they stable? So looking at the first one, we see x of t minus 2 and x of 2 minus t. And looking at this, we can conclude that this is not, or this system is not memoryless. Sorry, that was a double not. This system requires memory, because here we have an x of t minus 2, so that's a previous value, an x of 2 minus t. That's a bit of a previous and a future value. So the way that's not going to work. So this system has to have memory. It's requiring values other than the present. The other thing too is this system's not causal. For example, if we were to say t equals 0, we're going to have an x of -2 and an x of 2. X of 2 is a future value, so thus we can't have, we won't be able to have a causal system. So this system requires memory and is also not causal. Now, and it's kind of similar to the example I did before. On the left side, we have x of t minus 2. So if we were to shift that, if we were to do t minus t naught, and then the parentheses, it would be the same. But on the right side, we would have 2 minus t naught, and then we'd also have, if we did parentheses, t of 2 minus t plus t naught. So this system is also not time invariant. Now, the next thing we can do, though, is we can check for linearity. So if I was to take the right side and multiply it by some constant value, would that be the same as multiplying the left side by that constant value, which is true. The other thing, too, if I was to plug in, let's say t equals 0 and solve, and then also plug in t equals 1 and solve and add those together, would that be the same as y of 1 plus y of 0 plus y of 1? And that would be true. So this system is also linear. And then lastly, if we were to assume that x of t is a finite number, is always a finite value, and it doesn't go unbounded, then this system, that would mean that here on the left, x of t minus 2, well, x of t is going to be bounded regardless of any value of t. So that one's going to be bounded. And then x of 2 minus t, that's always going to be bounded as well for any value of t. So we have a bounded or finite number plus a finite number is always going to be a finite number. So that means y of t is bounded. It is stable. All right. Now moving on to the bottom problem. We have y of t equals 0 if t is less than 0. We have x of t, and then basically we have similar to the top, we have an x of t plus x of t minus 2 if t is equal to or greater than 0. So once again, looking at this, we can see that this requires values, an x of t minus 2, that is going to require memory. So this system is not memoryless. Now, interesting enough though, considering that y of t is 0 for t less than 0, because it only, and then if we look at this at the bottom part, x of t and x of t minus 2, never at any point is a t value required that we would consider a future value. So this system is actually causal. So, and then the next step to check if it's time invariant. So we'd have t minus 1, or t minus t naught, and we'd have to do that in every instance. That would be here. So that would be the t minus, or t less than 0, t equal to or greater than 0. So t here and t here. So this is where it would get a little interesting, because in this situation, it would not be time invariant. And that would be because we would be changing these parameters. But here on the other side, the parameters would not be changing if it was shifted. And then the next step, if it's stable, if x of t is bounded for all values of t, then the top part is always 0, so that's a bounded. And the bottom part is a bounded plus a bounded again, so that's also bounded. So this system is also stable. Okay. Any questions? Okay. Okay. So the next part I'm going to go over is something called an impulse response and a convolution. Okay, so an impulse response, so we can only gain impulse responses from systems that are linear time invariant, or LTI for short. And so impulse responses are very unique to those systems, and they can be gained from any system as long as it follows those rules. So if we have an x of t, and if we have a y of t, we can figure out and we can gain an impulse response that is basically, to best summarize it, kind of like the relationship between x of t and y of t. And methods of how you can calculate the impulse response is kind of covered later in Signals 1. That will be more in the second half of the semester, so I won't worry about it for now. The main thing to understand is that if you have an impulse response, and if you have x of t, you can determine y of t for any value of t. And the way that you can do that is by doing something called a convolution. So basically how it works, if you have an h of t, or if you have an impulse response, you can convolute it with x of t, and that will give you y of t. Now, how you do convolution changes depending on whether it's a discrete time signal or a continuous time signal. If it's a discrete time signal, then our signal y of n is going to be equal to the sum from k equals negative infinity to infinity, x of k, h of n minus k, which is the same as the convolution of these two. And an interesting enough, continuous time, it's basically the same. The only major difference is that it's now going to be an integral from negative infinity to infinity, and we're changing the k's to tau's, and we have a d tau at the end. So this equation is basically how you can determine the convolution of a signal. Now, I'm not going to go over any harder examples, but I am going to teach some, well, shortcuts. There's because you can always solve a convolution using this method, but that can always be a little grindy, it could be a little difficult, and it can be a bit confusing. So there's kind of shortcuts and methods and different properties of convolution that you can use that would make the process a lot easier and a lot simpler. So the first one I'll talk about is that convolutions are commutative, meaning you can do x of tau of ht minus tau, or you can do h of tau x of t minus tau. It doesn't matter, it's the same. So you can do x of t convoluted with h of t convoluted with x of t, it doesn't matter. It's the same thing. And that's true for any that you're given. Now the second property that I would like to go over is something we can call distributive. So basically, if you have an x of t, and if you can break it down into two parts, x1 of t and x2 of t, that are just the sum together makes x of t, then you can take the convolution of both parts. So you can do h of t convoluted with x1 of t, and you can do h of t convoluted with x2 of t. Doesn't matter, this is all the exact same thing. So if you're given complex signals, you can just break them apart. If they are additive, you can just break them apart and take the convolution of each piece. Okay, and now this one is probably the most helpful. So if you have, this is called an impulse function, and it's represented by delta of t. And on a graph, an impulse function is just basically, I guess, like a spike or a spear. It's of height 1, and it only exists at a certain value. So it's kind of like when you have like a discrete time value of, like, let's say at t equals 1, right? So you have a delta, so basically how it works is if you have a delta of 0, it means at the value 0, there's going to be kind of a pulse of height 1. And it basically means at that time, this will equal 1. And at all other values, it equals 0. So when we just have a delta of t, that means that when t is equal to 0, it's 1. And at all other values, it's 0. So basically, if you're having a convolution of x of t, and your impulse response is this delta function, then basically it's just going to be equal to the x of t. Makes no changes. Now, if you have a more complicated one where you have x of t times the delta response for a t minus t naught, well, that's simply just x of t minus t naught. You can skip the whole integral and everything and just go straight to here. And then, interesting enough, that also holds true if it's reversed. If you have x of t minus tau convoluted with x delta of t, that's still going to be x of t minus t naught. So this is an important property to understand. This helps save a lot of time on homeworks and all sorts of stuff as well. And then lastly, one of the most helpful shortcut that you can be given is you can have an x of t. And then let's say you have an x of t and h of t, and you're not really given an equation. Instead, you're given these two graphs. And you want to find the convolution of these two graphs. And they're rectangular graphs. So they're at a certain height, and they're equal to that height for the entirety of a certain duration, from t1 to t2 or t3 to t4. And you want to do the convolution. Now, you could write these out as equations. You could write them out as unit functions, and then have to do that. But that's going to be really messy and kind of terrible. So there's a much easier way of convoluting these two together. And basically, this is it. So basically what you do is you take a look at both of them, and you look at the widths of both rectangles. So that's your W1 and your W2. And whichever width is the smaller of the two, we'll say in this example it's width 1, we take note of that, and we use that to calculate the height of this new polynomial. So basically how it works is you take the far left value of where this shape will begin is going to be T1 plus T3. And then the other side is going to be T2 plus T4. So basically you're adding the sides of the rectangles together to get the whole width of the new shape. And then you take this width that is shorter, so width 1, and there's going to be a triangular shape up to width 1. And then the same, the next, where the next slope starts is going to be width 2. And the whole height of the system is going to just be the height of the first one times the height of the second one times the width of the smaller width of the rectangles. Now this is true where y of 1 is less than, or where the width of the 1 is less than the width of 2, and it could be either one, just as long as one of the widths is shorter than the other. But then we're left asking, what happens if the widths are equal to each other? What would you do in that case? So in that case, you would do pretty much the same thing, but basically it would form, instead of forming this, I think rhombus shape, it would form a triangle. And basically the bottom of the triangle would just be equal to 2 times the width of the rectangles. And the peak of triangle would just be the width of, or from the beginning of the triangle to the peak would be the width of either of the rectangles. Okay. Any other questions or anything you wish for me to go over? Okay, sweet. So I think for now, that's all I have planned for our for my training tonight, but I can stay on and we can cover some more questions. Oh, sweet, thank you. But if you wish to go, you're free to go.